So the next presentation will be done by Professor Dr. Zaeh. He's called, Professor Zaeh is from the Technical University of Munich, or the TU, and he will present about a presentation called Artificial Intelligence, Just a New Keyword, or Can Production Technology Profit from It?
Yes. Good morning, everyone, and thank you very much for the word here, for giving me the opportunity to present to you. Now, I did share my screen and click to presentation mode. Just to check, can everybody hear me and see the first slide?
Yes, we can.
Wonderful. So I think, in fact, this presentation does quite well complement what we just heard from Dr. Voss. It was primarily meant to give you an impulse, a thought-provoking impulse, if you wish, on how we can benefit from artificial intelligence when pursuing those goals that were mentioned for the workshop. In terms of reconfigurability and therefore application of robots. And indeed, digitalization is a basis for what I'm telling you now about artificial intelligence. I think, well, I raised the question whether it's just a new buzzword or a new keyword. I think it's more than that. I would like to answer the question in the very beginning. I think it's much more than that, and it has a huge potential in order to bring us closer to the goals mentioned for this workshop. I'd like to first define what we mean by intelligent and artificial intelligence, categorize it into those three keywords that you see under number 2, chapter number 2. And then the main part of my presentation is to give 3 examples out of our research at IWB that underline and make clear how artificial intelligence can be implemented in production. And if there is time left, I'll also introduce the Institute. Intelligence. What is intelligence? There is a definition for intelligence of humans, which is associated with capability to learn, capability to understand, to develop solutions for problems and things like that, the capability of reasoning and so forth. And it's frequently studied mainly with a focus on humans, sometimes also with a focus on animals and even plants. We have a number, we have a figure to quantify it, which is usually acknowledged, which is the intelligence quotient, which relates the intelligence of an individual person, to the intelligence of a peer group, and can determine or can tell whether this person is above average intelligent or below, and so forth. And with that, we had the idea, we as researchers had the idea to also make machines intelligent in the sense that they can learn, that they can solve problems, and so forth. And computer science started to call this artificial intelligence, machine learning, and even deep learning. And the categorization is such that deep learning as a method of machine learning, which uses connections, learns connections from a multitude of data through complex neural networks, is the most sophisticated type of machine-based intelligence. Apart from that, we define machine learning as algorithms that learn from data to make predictions, to interpolate or extrapolate data. And artificial intelligence as a whole also includes less sophisticated techniques and algorithms, even those that we call genetic algorithms, which are very simple ways to optimize numbers, functions, or whatever on a heuristic basis. With that definition, based on that definition, I already come to the examples that I'd like to show you. And the first one stems from production planning. Then I have one from processes, from our processes. In particular, we do welding research. And for welding, we also need to be able to measure the depth, for example, of a melt pool or of a keyhole in laser-based welding. Before I get to those examples, I'd like to show you our view, however, which I think is quite common sense, our view on different levels of production. Starting from the basis, we have production processes that really create value. These processes need a machine or a station to be implemented and to be executed. Several machines together form a cell, multiple cells a system, those a segment, and all those segments together in a company we usually call site, and then we have company networks, whether legally belonging together or not. And on all these levels of production, we have plenty of fields for the application of artificial intelligence. And these titles here show you what we do in terms of research at IWB in order to bring artificial intelligence really to the shop floor, to the site, to the machine, and to the process. And out of those, I picked 3 examples. Indeed, they foster the achievements of the goals that are addressed in this seminar here, because with more intelligent machines, we are better in terms of reconfigurability. And the other keyword is digitalization, and digitalization really is a basis for artificial intelligence application. Without digital data and without a sufficient amount of data, we would never be able to apply those methods. So now I'd really come to the first example, which stems from job order planning and from the cooperation with a supplier of household equipment like dishwashers and electric stoves. And we worked together with one of their plants where they had the problem to manufacture different models of dishwashers. And for that, they had a total of 8 assembly lines, here marked L1, L2, L3, line 1, 2, 3, and so forth. And the issue was, how do we do the job order planning for one production day, for the shifts of one day, on the basis of setup codes of those dishwashers in order to not overload the capacities of the lines, and in order to minimize the costs for changing the setup on one line. All those lines have individual capabilities. There are more sophisticated ones and simpler ones. And the particular dishwasher models create setup costs and changeover costs, like from one model to the other. And this was a job done by a human, which took several hours to find a good solution. And we suggested to do this based on a genetic algorithm, which starts with an initial population and then calculates a fitness function. Now, you all know how these algorithms work. The decisive thing is to define a powerful fitness function, which in this case is this term here over the, or a sums over the costs for changing from one order to another, depending on the particular population of the first line order allocation to the lines. And these changeover costs can be calculated based on the setup codes I mentioned here. And the second term more or less penalizes a capacity load of the line. Some capacity load is tolerable by just working overtime, but too much of overload has to be penalized heavily. And now this algorithm just is executed several times, selects a number of the best individuals, which are created randomly by changing the initial population. This way creates the next generation, evaluates the individuals with this function, and then goes back by mutation and reproduction and selection of the best fitness functions in order to finally minimize those overall costs. And once a certain threshold is not exceeded anymore, we have the final result. And executing this shows that within several calculations, or just a handful of calculations, we achieve a very good result. This is the performance graph of different executions. And even if you start with a very bad initial population, you end up with a very good result here within a calculation time of 10 minutes or so, which is an extremely good support for the individual to execute this job. Will the individual lose the job? Question mark. Certainly, there may have been concerns. However, I think this is a very good instrument because it allows this individual to use his or her time better and more productively than just by trial and error in order to come to this execution sequence. So it's a benefit for production. My second example is from welding. As I mentioned before, we do research on laser-based welding. And for this process, we often have the task to weld a framework, here symbolized by just those 4 bars that have to be welded together with this kind of overlap weld seam. And the issue is that from laser-based welding with heat being introduced into the structure, we have distortions, we have high distortions, and the goal is to minimize those distortions in order to close the frame with this final weld seam without having to bend it. Now we have models available to simulate the thermally induced distortions. However, based on finite element method, this takes very long to calculate, weeks, if not months. And this is, of course, not feasible for an industrial application to enumerate all the possible welding sequences and parameters in order to find an optimum out of that. My former PhD students, Alexander Schober and Alexander Belitsky, had the idea also to use an evolutionary algorithm in order to change the parameters, but not use a finite element model, a powerful and accurate finite element model, only to create a training data for an artificial neural network, which is based on neurons that you can see here. So an artificial neural network in order to learn from what the result was out of a finite element calculation. And they had to do the finite element calculation only for a very limited number of possible combinations of parameters and welding sequences. And by then learning and taking the predictions from the artificial neural network, they were able to reduce the remaining distortion here vertically, that's the one that's important, vertically, from a few millimeters to a range where this is no longer visible. This gap here was left intentionally so that it can be demonstrated more easily. And you can see that in vertical direction, those ends of the framework are on the same level with the optimized parameter setting. So the artificial intelligence will allow us to drastically reduce the effort for simulation for this particular problem. And the third example is coming out of our most recent work on weld depth measurements, for which we have adopted a recently invented technology, which is called optical coherence tomography, OCT. The issue is depicted here, where we have a welding seam in an overlap configuration. And with this optical coherence tomography, it's possible to, in quotation marks, look into the keyhole, which is opened by the laser. It's basically a steam capillary here in the weld seam. Along the weld seam, the laser is moved from left to right in order to create the weld seam. And with an interferometer that you can see here and a dichroic mirror, we can insert a measuring beam into this keyhole and in quotation marks, as I said, look into this keyhole. And from that, we get an interferometric result depending on the actual depth of the keyhole, which has to be deeper than the upper layer of the sheets, in the upper sheet thickness, in order to reach the lower sheet and really weld them together. Now, the problem is that this keyhole signal is heavily scattered, as you can see on the left-hand side. And as a human, you would say, okay, yes, let's take a mean value, somewhere over here. And this is quite a good indicator for the keyhole depth. However, for a machine, for a computer, it's difficult to benefit from this kind of scattered signal. And in order to deal with it, we designed an artificial neural network in order to evaluate all the data. And we supplied for the artificial neural network, we also supplied micrographic cross sections of the actual weld seam with the measured weld depth. And from a limited set of training data, the artificial neural network could learn how to deal with this as I call it, point cloud, in order to come to a reliable representation of the weld depth. So that is what the system will finally supply, what the system will provide to the user in order to determine whether the weld seam was deep enough to connect the two sheets. So this was the third example, and I think there are 2 minutes left to show you 3 slides on IWB. We are not located in the city center of Munich, but about 14 kilometers north of the city center, here on a research campus which started to evolve in the 1950s with the inauguration of this research reactor, which is a neutron source in order to do neutron-based research in physics. And later on, the TUM, Technical University of Munich, Physics and Chemistry Department, Mechanical Engineering, Maths and Computer Science were also relocated to this campus here. We are connected to the underground metro network of Munich. We're in this building over here in this wing as IWB. We do research on all levels of manufacturing, on machine tools and industrial management, with those levels depicted in one of the early pictures of my presentation. I'm coming from the machine tool sector. I look back at 6 years industrial career with a German machine tool manufacturer, but nowadays do also research on cutting, joining, and additive manufacturing. And here you see our laboratory with about 3,000 square meters of laboratory space. And we have about 80 PhD students supervised by 2 professors, with a total staff of approximately 100 people, always fluctuating from month to month, because we have new people coming aboard and others who leave after receiving their PhD. I hope I could give you some kind of an imagination how our goals can benefit from artificial intelligence. Thanks again for giving me the opportunity to talk here. And I'm, of course, happy to answer your questions. Thank you very much.
Thank you, Professor Zaeh, for this very interesting presentation. Of course, you can ask questions in the chat. There is already one from Professor Troussier. How do you integrate learning process by evolution in the learning database to enable evolution and reconfiguration in the genetic algorithm for job order planning?
How do we integrate that? Well, how do we integrate that? As mentioned before, the starting point is the orders that are to be processed on a particular day, meaning the orders for the shop floor to assemble dishwashers with a certain quantity and distribution over the different models. And this data can be taken from the enterprise resource planning system and then supplied for the genetic algorithm. And whatever the genetic algorithm will supply as a result then has to be entered in the ERP system by the human. So there's still a human as an interface between the system. However, one can think about also automizing this data transfer in both directions. Does that answer the question?
I think so. Thank you. There is another question from Eldar Shakirov, sorry for the pronunciation. Thinking of the reconfigurability, maybe in the broader term, how do you see the future of distributed manufacturing system? Which one or two applications of AI will be critical in this regard?
Meaning distributed systems in the sense that we have different factories, even in different countries and different continents, to supply each other? Is that distributed manufacturing is meant in that sense?
Yes, the networks.
Yes, the networks. Well, if so, I think that this Corona or COVID-19 crisis puts some question marks towards these approaches that we have pursued in the past with purchasing cheap supply from, let's say, the Far East or other countries. And I think artificial intelligence can support us also in decision making, for example, by helping to evaluate the risks of such supply chains and their vulnerability for future similar crises like that one.
Thank you for your answer. We also got one other question. I think we've got time left only for one of the questions. It's from Isham. I don't have the rest of the name, sorry. How difficult will it be to transfer those developed AI technologies to different use cases?
A simple answer, I think fairly easy. It will be fairly easy. You need a good idea, or you need a view which are certain problems that can be addressed by those algorithms. For this here, for the job order planning, I can say that this was really adopted by our industrial partners. This made its way to the shop floor, to the office of the shop floor supervisor, and is being used there. And I see the purpose of this presentation to be an eye-opener. Think about where have you similar problems where currently we do trial and error. We do optimization and we execute our tasks by just trial and error, which a machine can do as least as well as we can. I can only supply an eye-opener, and then we have to go through the factories with open eyes, look at how people do their jobs today, and then try to find the right, the suitable methodology from this set of methodologies that I introduced.
Thank you. And since we've got 1 minute left, I get to ask my question. It was about when you presented this job order planning, partly unsure for the input, but do you think this tool could be used as a decision aid, and the human employees could help input intelligence in the system and to use it as a head?
Yes. Honestly spoken, I have not been thinking about that. But as you ask the question here, one could certainly think of connecting this with even more sophisticated intelligence. This in the computer is nothing else but also trial and error, as you could easily notice. It's also trial and error. And trial and error is the simplest form of intelligence, I think. Like if you, for example, try to insert the key in your door at home and it doesn't work, you try a different key, or you just try to do it otherwise with a different position of the key. So trial and error, it's a simple form of intelligence. And here you could certainly think of learning with an artificial intelligence, learning certain patterns, which kinds of sequences are more favorable, which ones are not, and then even improve the performance of this simple algorithm.
Thank you for your answers and your presentation. It was, yeah, we're very grateful to have you presented here.
Thank you very much. It was my pleasure.